So this is the physical setup for the bell crank lever. So you can see here, this is the horizontal arm that is called as a weight arm, and this vertical arm, this is the tension arm. Okay, this tension arm, it is connected with the spring balance, and here we can see the arrangement, which is a nut and screw arrangement. So with the help of this arrangement, we can increase or decrease the tension. So its three body diagram will be like this, which is drawn on the board. So this point, it is the hinge point, or this is a pivot point. So as the hinge point, it will offer two reactions. One is a VA, and second is the horizontal reaction, which is the HA. Okay. So the bell crank lever, it will allow the free rotation in the clockwise direction if you add the weight. So in the principle of moment, your equation will be summation of moment in the clockwise direction. It must be equal to summation of moment in the anti-clockwise direction. Okay. So we have to verify this principle by using the bell crank lever. So you can see here the rotation. So if you add some weight, then this complete lever, it will rotate in the clockwise direction. Okay. So you can see here, it will disturb the original equilibrium. So there is one pointer. Okay. So this pointer, it must be aligned with this point so that it is in the perfect equilibrium. So right now the equilibrium is disturbed. So we need to bring this point with in line with this point. Okay. So we have to increase the tension in the spring balance. So we can increase this tension by adjusting this nut and screw arrangement. So you can see it is in perfect equilibrium. Okay. So at this condition, we can use this equation. Summation of clockwise moment, it is equal to summation of anti-clockwise moment. So you can observe in the free body diagram, this is the weight W. So it is at distance X. And here we have the tension in the spring balance. So it is at distance Y with respect to the pivot point. So this is the Y distance. Okay, so this distance, which is shown here, it is a fixed distance. That Y will remain same. Only we will change the X. That means we will shift the weight towards the point O or away from the point O. So your equation for moment will be that W into X, this is a clockwise moment, and this is the anti-clockwise moment, which is a T into Y. So for perfect equilibrium, this equation must be satisfied. So this is the X distance. So actually during the experiment, you can directly measure this from this scale. There is a scale given on the weight arm. Okay, so this is your complete procedure. So for the observation table, your first column, this is the weight column, which is W1, then distance X1, then second weight W2, its distance X2, then distance Y, where the spring balance is connected, and the tension in that spring balance. So the formula is final tension minus initial tension, and it will be in the kg if you are taking this weight in the kg. Okay. Then T theoretical. Then this is the clockwise moment summation, and this is summation anti-clockwise moment, and this is the percentage error. Okay. So for that, you can refer this free wall diagram. So here, this is the moment point, which is the point O. At this point, this is the spring balance tension, okay, which is a T. This distance, this is the Y, which is the fixed distance. Then at this point, we have the weight W1. At the second point, this is the weight W2. This is X1's distance, and this is X2 distance. Okay, so we are measuring X1 and X2 with respect to the point O. So here, equation will be, I will write the equation for summation of moment in the clockwise direction. So this is equal to W1 into X1 plus W2 into X2. Okay. And the anti-clockwise moment, which is summation of moment in the anti-clockwise direction. So there is only one moment, which is a T into Y. Okay. So this T value we will get from the experiment. Okay. Because we have to note down that value from that spring balance. Okay. So here we have to find out what is the theoretical value. So theoretical value you can find out by using the equation for the moment. So T into Y, it must be equal to W1 into X1 plus W2 into X2. Okay. So T is equal to W1 X1 plus W2 X2 upon Y. So this value is theoretical value for the tension. Okay. We have to compare this value with the experimental value, and then you can find out the percentage error. Okay. So this is your complete observation table. So we will select the value for W1 as a 1 kg. Okay. Then its distance with respect to point O. So this X1. So this is equal to, so right now it is in meter. So it is 0.3 meter or 30 centimeter. Then weight W2, again select 1 kg. Its distance with respect to this point O. So I will select this 20 centimeter. So this is, sorry, this is 60 centimeter. So it is a 0.6 meter. And distance Y, this is fixed. So this distance Y, this is equal to 45 centimeter. So this is 0.45 meter. Okay. So this tension we have to find out from the experiment, and theoretical we can find out here by referring this equation. So here theoretical value, so T theoretical, this is equal to 2 kg. Okay. And this tension, this is equal to T is equal to TF minus TI. Okay. So I will explain what is meaning of TF and TI. So just observe this spring balance. So in this spring balance, if there is a zero weight on this bell crank lever, okay, theoretically, this T value or tension in this spring balance, it must be 0 because there is no weight on the spring balance, sorry, on the horizontal arm or on the weight arm. But if you don't add any weight, that is a dead weight, still there will be some weight, that is the self weight of this arm. Okay. And because of this self weight, some moment will be created about the hinge point. Okay. So in order to balance this moment, we need to create some initial tension. Okay. So that initial tension is nothing but the Ti. So it can be 0.5 kg. Okay. And after you add the weight, we will create more tension by adjusting the screw. So that will be your final tension value. Okay. So for time being, just assume the final tension value as a 4.5 kg. Okay. So net tension, this is equal to Tf minus Ti. So right now this is 4 kg. Okay. So this is your net tension value. So in this way, you can note down the reading. So initially we have to observe what is the initial tension required to maintain the equilibrium when we are not adding any weight. Okay. So that will be our initial value. After that, add some weight, 1 kg, 2 kg, and again adjust the tension. Note down that tension for equilibrium. Take the difference. It is the final tension value. Okay. So in this way, you can find out this difference, or you can directly put the value of tension T. Okay. So from the experiment, we have got this value as a 1.9 kg. So required value is 2 kg. From experiment, we get 1.9 kg. And then you can write this equation, summation of clockwise moment and summation of anti-clockwise moment. Okay. So summation of clockwise moment, this is just a theoretical value. Okay. So this equation. And anti-clockwise moment, this is your experimental value. Because T we will calculate from the experiment. Okay. So this value will be, so right now the theoretical value, that is and clockwise moment. So this is 1 into 0.3 and plus 1 into 0.6. So it is 0.6. This is your clockwise moment and unit is kg meter. Okay, we are taking the weight in kg only. Anti-clockwise moment, this will be, we have to use experimental value of tension. So this is 1.9 and y is 45. So this is 1.9, 0.45. So anti-clockwise moment, this is equal to, so this is 0.85. So just check this value, clockwise moment. Okay, sorry, this value is 0.9. This is 0.9 kg meter, which is a clockwise moment, and anti-clockwise moment is 0.85 kg meter. Okay. And the percentage error you can find out as you have to find out this difference. Okay. And divide it by the theoretical value. Okay. So actual value required is 0.9. So percentage error is, just I will write here, percentage error. So here difference in theoretical moment and the experimental value upon the theoretical moment. Okay. So right now this is equal to theoretical moment is 0.9, experimental value is 0.85 upon 0.9. Okay. That means difference of this value and this value divided by this value. So this is equal to So this is 0.055. Okay, and we need percentage, so we have to multiply this by 100. Okay, so this is equal to 5.5%. So from the experiment, we get this difference as a 5.5%. So this can be due to the error in the measuring device, which is the spring balance. Okay. So in this way, you can verify the principle of moment. So your equation for the moment is, this is the clockwise moment, this is the anti-clockwise moment. Theoretically, these two values must be same for the equilibrium. So when you complete the write-up for the experiment, so your first page, so this is about the M, then you have apparatus, okay, then the theory or the procedure. In the theory, just we have the equation, what is the principle of moment. So after that, we will just write the procedure, okay. So then we have the observation table, okay. After observation table, we will show this sample calculation. So just show two calculations for two readings. So in this calculation, we will calculate the clockwise moment, it is the summation of clockwise moment, okay. After clockwise moment, we will calculate the T theoretical. I have given the formula for T theoretical, okay. Similarly for second reading. And in the last page, there will be result or the conclusion, okay. So right now we have to just verify the principle of moment. So we will give the conclusion, okay. So in the conclusion, we will write, from the experiment, it is found that the clockwise moment, it is nearly equal to the anti-clockwise moment. So hence we have verified the principle of moment by using the Bell-Crank apparatus. So this is your conclusion for the experiment, okay. And on the first page, before the aim and apparatus, there will be the diagram. So you will draw the diagram for Bell-Crank lever. So this is your apparatus diagram, okay, it's complete apparatus. And just below this, you will draw the free body diagram, because this calculation, it is entirely based on this free body diagram. So like this is tension, some distance x, x1, x2, and this is the hinge point, which is a VA and HA. So actually here we are not calculating HA and VA, okay. So just we are interested in whether clockwise moment it is equal to the anti-clockwise moment, okay. So this is your complete experimental write-up for the first experiment.